a point or two. If you see this, in the example where we said K is a property, right, and it's our predicate term, and the property is having knowledge, then this would be read, this statement would be read for, we know that this is for all, right, for all x, remember, for all x, the universal claim, for all x, and that's symbolized by the first part, right, that's symbolized by this, right, so for all x, then you say x has knowledge, right, for all x, x is said to have knowledge, right, x has, which is symbolized by, so this is read for all x, which is that symbol, x has knowledge. X, the subject, has the property of being knowledgeable. Okay? So for all x, x has knowledge. That's how that is read. The next thing that I want to show is this. How is this read? Well, you know, take a shot at what you think. How do you think that would be read? We see that this part's the same, so it should be the same. It's just different, right? This would be for some x, which is represented by this, right? For some x, which is represented by this, x has knowledge, which is represented by, right? So for this is this symbol, this structure means for all x, x has knowledge. This means for some x, right, which is that x has knowledge. Pretty simple. The next thing that I want to do is to show you sort of the relationship between two terms. These two things will mean exactly the same thing, though the symbolization will be different. So the claim is this: for all x, comma, x is an f, whatever f might be, right? So this claim, for all x, x is an f, can be symbolized two ways, right? And again, I want you to know what these symbolizations might be, because depending on who's giving the lecture, there could be some confusion as to how to read or make sense of the symbolization, especially at an introductory level. The first is this, right? Right? You can, this means exactly this, right? For all x, x is an f, right? X is an f. For all x, x is an f. There's also another way of symbolizing it, right? And we know that this symbol is the same as this symbol, right? So it's exactly the same as doing, right? Exactly the same stuff, right? They mean exactly the same thing. This means and this means, they both mean for all x, x is an f, right? That's how it's read. For all x, x is an f, right? If we were to substitute f with, let's say, k for knowledge, right? Then it would be for all x, x has knowledge, right? That's how it would be read. This would just be for all x, x has knowledge if we substitute, or we change the predicate term, right? And the predicate term went from f to k. But you get the idea. Okay, so hopefully that clears up some confusion. Next is the negation, which is important. And again, I'm sort of breezing through this because there's a lot of information that's already out there. This is just more of a sort of clarification video, I guess. For example, you can have the claim let's say we have the claim for all x, x is not an f, right? Imagine we have the claim for all x, x is not an f. The question would be, how is that symbolized, right? Well, we recognize that for all is going to be either this or this, right? So for all x, right, x is not an f. Well, what we would do is we would have, in this case, not an f. Right? For all x, x is not an f. Right? So, and obviously it would be the same, right? So for all x, and I don't want to confuse it anymore, you know that these symbols are interchangeable, but if we write for all x, x is not an f, it's symbolized like this, right? For all x, x is not an f. That's, and you can put in whatever that predicate term might be. Let's do the existential, right? So imagine that the statement was for some x, and I forgot the individual constant there, x is not an f, right? So imagine that it's for some x, x is not an f. It would be for some x, right? X is not an f, right? So for some x, x is not an f, would be symbolized like that. So hopefully pretty basic. Next point, really quick, 2 more points. I want to talk about scope in free and bound variables. So that concludes negation. I don't think there's anything super difficult about that. Next is scope. This will factor into later discussions. Okay, so let me just read this, see how this goes. Because there's a first. Okay, so imagine that we have this, right? For all x, x is an f, right? So we have for all x, x is an f. And I wanted to know what the scope of this claim is. Well, I would have to look at what's known as a complete formula, and this will make sense in a second, right? And the question is, what aspect of this statement, right, is associated with this claim, this universal quantifier? And we see that it's f of x. So if we wanted to talk about the scope, right, the scope of this universal quantifier in this example, and I'm going to give you a couple of examples, we would see that the scope of this universal quantifier is f of x, right? So the scope of this claim, the scope is the scope is, that's the scope. I'll give you a couple of examples you'll catch on sort of quickly. I'm going to give you two more examples. Okay, imagine that we have this. For all x, well, I don't like this. Actually, we'll use this so we don't confuse it. For all x, okay, so imagine that same thing. Remember, we know that these are interchangeable. For all x, f of for all x, if x is an f, then y is a g, right? Well, how would we make sense of this, right? For all x, if x is an f, then y is a g. With respect to the scope of, and we're asking about the scope of the quantifier, we recognize that the scope still is the same, right? The scope is the same because the scope sort of covers this approach. It's bound, in a sense, to the quantifier, right? This universal quantifier is bound in this regard, right? So we would say that the scope is f of x, which is pretty simple. I can write exactly the same thing though. I can write exactly the same thing. I can write this. Wait, let me do it right. I can bracket it and say f of x, g of y. If I were to write it like that, right? If I were to write it like that, or obviously it would be exactly the same thing. I could write it like this. It means exactly the same thing. We recognize now that the scope is broader, right? The scope for both of these include f of x and gy, right? X is an F and G is a Y. The scope includes X is an F and G is a Y. That's included within the scope of both of these, right? So it's pretty easy to see because these brackets, right? These brackets associate both the antecedent and the conditional with the universal quantifier. Same thing with the universal. I mean, these quantifiers are exactly the same. People symbolize it differently, but X is an F. If X is an F, then Y is a G. We see that this is, in a sense, bound to, associated with the universal quantifier. So I just wanted to put that point out. And then the last point has to do with bound and free variables, and that will conclude this sort of very, very introductory account of predicate logic. Imagine, and I'll go back to the same examples, imagine that we have this example, right? We have imagine that we have this. For all x, if x is an f, then y is a g. We need to associate, we need to determine which variables are bound, which variables are free. Our variables here, and actually instead of using variables, it'd be more accurate to call them the individual constants, right? The individual constants here are x and y, right? X and y are right, in this example, x and y are individual constants, but as we've seen from before in determining our scope, x is going to be bound in this example, right? X is going to be bound, and y is going to be free. Why is y free? Because y is, in a sense, not within the scope of the quantifier, right? Y is not within the scope of the quantifier. However, let's take this example where you have, for all x, if x is an f, then y is a g, right? And we bracket it, then we realize that we are saying that for all x, if x is an f, y is a g, is attributed to the universal quantifier. Insofar as we attribute it to the universal quantifier, then both of the individual constants, right? Both of the individual constants, y, x and y, are bound, right? So x becomes bound like before, but also y is bound, right? So they're both x and y are bound. And again, I didn't want to go into too much detail and sort of do an overkill video because it's already out there. There's a lot of videos on predicate logic. I'm not going to make just another video on predicate logic for the sake of making a video on predicate logic. There's actually pretty good videos on predicate logic. What I saw, however, was that the symbolization between videos, right? One video would talk about universal quantifiers and use this notation system. Another video would talk about universal quantifiers and use this notation system, and it can get very confusing. And the point of me, and also with the biconditional use of symbols, the point of me making this video is to say that they're all saying the same thing. It's not an inconsistency, it's just a difference in sort of style in going about doing it. So if you're very interested in predicate logic, watch another video to learn how to really get into it. Predicate logic. What I might do, because I haven't seen too many videos on predicate logic and sort of the deduction, sort of the justification for universal instantiation and existential generalization, that type of stuff. I'm going to look and see if I see videos out there, more of the rigorous sort of deductive accounts. If there aren't any, I'll make one. But there are tons of videos in telling you how to go about symbolizing particular phrases or words or passages and so on. So I'm not going to do that. Hopefully this was helpful. And with that, I'm done. So thank you for watching my video. I'm Dr. Jason J. Campbell. Goodbye.